when I heard about this conference, I immediately thought about Abbaco mathematical culture as an example, as a good example of what a mathematical culture is and can be. So while this is a bit more distant in the past on mathematical practice, I hope it will raise the right questions concerning what mathematical cultures are. Okay, I will first raise some general questions about mathematical culture, and I propose a framework from mathematics education on mathematical cultures. Then I will give some more information about this Abbaco tradition, and conclude with some of the relevance for our contemporary understanding of mathematical culture. So, general questions are: what constitutes a mathematical culture? When can we speak about a mathematical culture? What is the relationship between mathematical cultures and society in general? How does it emerge in society? What is its role in society? How is it supported, or how does it support society? And if there are many mathematical cultures at the same time period, how do they interact with each other? I think this example fills in some of these questions. The framework I will be adopting is from Alan Bishop, from his book Mathematical Enculturation, already from '88, in which he starts introducing mathematical cultures with some statements like mathematics is not a set of abstract truths independent of society and culture. Mathematics itself is a cultural product, and mathematics can have different interpretations, values, and uses in different cultures. These are statements that will not offend anyone in the audience, I suppose. What he's adding to this is that is a criterion for him to speak about the mathematical culture when it is maintained by what he calls enculturation. And he defines enculturation as a creative, interactive process engaging those living in culture with those born into it, which results in ideas, norms, and values which are similar from one generation to the next, but can also change, of course, between generations. So he, as an educator or someone interested in mathematics education, he places much importance to this role of enculturation. He also defines 6 universal activities of a mathematical culture: counting, locating, referring to spatial notions, measuring, designing, playing, and explaining. And explaining here refers to classifications. Now, if you look at this Abbaco tradition, first in a narrow sense, this is a tradition of mathematical practice, mostly in northern Italy in the 14th and 15th century. But more general, it has to do with the introduction and use of Indo-Arabic numerals throughout of Europe, so in a broader sense, and by lay culture. This is an important aspect. In every aspect related to Bishop's view on mathematical culture, it's a very good example. It is strong, very strong in this enculturation and a formal practice of teaching. It very well represents these 6 universal activities, and it was very supportive of the social context of that time. Which was a context in which there was a transformation in economic practices from traveling salesmen, traveling merchants, to a sedentary economy, which needed banks and bookkeeping. These 6 activities of mathematical cultures are very well represented in the Abbaco tradition. Counting, we had competing systems, one with hand reckoning, and then of course calculation with pen and paper using these Indo-Arabic numerals. Locating was represented by practical geometry, including use of instruments and design of instruments. measuring by the surveyor tradition. Many of these treatises deal with measurement of plane figures and also contents, volumes, like gauging, determining the volume of a barrel. Designing, perspective is not really a part of this tradition, but is very well connected to it, like Alberti in the beginning of the 15th century. Fortification also grew out of this tradition, designs of machines and things like that. Playing is very well represented by recreational programs. There are many references to other games like chess, even conjuring. And explaining, as defined as classification, is very well represented by tables, calendars, and all kinds of emblematic devices. It's also important to distinguish here between scholarly and non-scholarly traditions, as the Abbaco tradition is what is specific and non-scholarly tradition, or in the terminology of Jens Heure, a sub-scientific tradition. And they are quite different in several aspects. Scholarly tradition is, especially at that time, very scholastic in nature. It is based on some authoritative text with commentaries, like in that time the quadrivium taught at universities. It was taught or written in learned languages, in the medieval time Latin. This tradition is very protective and conservative. It is supported by authorities, emperor, church, patrons, and it is very well represented in the history of science or history of mathematics. On the other hand, the sub-scientific tradition is basically an oral tradition. If there are excellent texts, they are written in vernacular. Knowledge is disseminated through master-apprentice relationships. The traditions are very open to foreign influences. They are supported by lay cultures, in this context, merchants, surveyors, craftsmen, and artisans. And it's usually underrepresented in the history of science. To put some names on it, the Latin scholarly tradition, the authoritative texts were from Boetius from the 6th century, but you also had these practical calculations which were done on the Roman abacus and derived from Roman times. There was some kind of reform by Gerbert in the 10th century, and then you have some names which are more or less known. Fibonacci appears in both. He was writing in Latin, published treatises, but he was very well acquainted with his sub-scientific tradition. And these are some names of Abbaco mouses, which are probably much less known. Sorry? The historiography is rather sparse, because not much has been written about it some centuries ago. We have Guillaume Libri, who was a collector of books and manuscripts, much of which he acquired by stealing them from libraries. And he owned a lot of Abbaco manuscripts. And he was the first to put some transcriptions in his volume work on the history of mathematics.
Sorry, Piero della Francesca, how does he go in this sub-scientific aspect?
Well, he wrote two treatises on arithmetic and algebra, which fit perfectly within his tradition, though he was also an artist. Compagni was also a book collector, and he had his own journal in which several references and descriptions are made of this manuscript. But it's only from the 1960s with Gino Arrighi that we have access to these manuscripts, which were kept at libraries, and also especially by the PhD of Warren van Egmond and his catalogue he published in 1980, in which the whole corpus of about 250 manuscripts became known. And then several people have been working on the transcriptions, and Jens Heure published the first translation of a complete work. These are some, about 20 of the 250 manuscripts have been published either in Italian or in translation. The common story is that this tradition emerged from some important works, being the works of Algoritmi. On the one hand is arithmetic, Dixit Algoritmi, and on the other hand is algebra. There's also a geometry with some text of which we only have a Latin translation. And the other big well-known work is the Liber Abbaci, containing both arithmetic and algebra, and the Practica Geometrie of Fibonacci. Now, this is typically from a scholastic idea that this is an oral tradition, so it's wrong to put to explain it as the consequence of some great books. And the current view we now have is that the Fibonacci and Liber Abbaci was more part of this tradition than the origin of this tradition. It did not emerge in Italy, but mostly in the Provençal and Catalan region in the 12th century. It has been very much influenced by Arabic sources, Chinese, Indian, Byzantine influences, and quite interesting is that it's a very coherent practice of writing and doing mathematics during 2 full centuries, the 14th and 15th century. I hear some more arguments against the idea that it's just derived from Arab mathematics or from Algoritmi, namely that Fibonacci himself refers to Magister Castellanus, a Catalan master. There are also several internal reasons why the Abbaco algebra is different in characterization than from the original works of Algoritmi. The social context in which this emerged is that of Maestro d'Abbaco, who were teaching in so-called bodegas in the mercantile cities of northern Italy. They went often through several family relationships, like the Calandris. They had 5 generations of masters. They enjoyed a high socio-economical status, middle class or even higher middle class. They were teaching to sons of merchants and artisans, and some of them were quite famous, like Dante Alighieri and Leonardo da Vinci. They were either employed by the city, the larger cities, or working on a private basis. And we are fortunate to have these manuscripts because they were collected by the rich bankers and merchants like the Strozzi family. Some of them are also nicely illustrated, which makes it more attractive to collect. These schools, Elisabeth Olivi did some archive research on this, and the earliest record we have is from the late 13th century. There were about 20 schools active in Florence alone during this period, and at some point at the beginning of the 14th century, there were 1,200 students employed for going to the schools in Florence alone. Florence was then a city of 50,000–60,000 people. Students were boys aged 10 to 14. They went to the school after grammar school when they could read and write. And they were taught in 7 nude, we call it nude. And we know this because one manuscript is explicitly describing what kind of material was being taught. It was numeration, addition, subtraction, the tables of multiplication, then division with increasing levels of complexity, operations of fractions, the rule of 3 with business applications, the monetary system, and problems of exchange. Now, these subjects also are contained in the first chapters of these treatises, but they go beyond that. They also involve other problems and mostly algebra, which were not taught at these schools. So these Abbaco books and treatises were not used for teaching. They were more a kind of trade secret exchange between masters and giving from master to apprentice. A typical book contains 200 to 600 pages. This is an example from the Plimpton collection. They are divided, we start with several chapters, and this is the material that could have been taught at schools, but then they move to problems and problem solving. And the bulk of the treatises is just about problems and problem solutions. This is an example of a hand trigonomy, which you find in almost every manuscript, but still practiced all the time. The business problems start with the rule of three, exchange of money, barter, and these are all real situations, practical situations, which were part of the mercantile practice at the time. Partnership or partnership in time, in which the profit has to be divided, interest and discount, repayment of loans, allegation problems of metals and mixtures of liquids. Then you have the algebraic problems, the more theoretical ones, derived from Arab algebra. Divide a number into two parts given certain conditions, or find me a number given certain conditions. Numbers in proportions, numbers in continuous proportions, indeterminate problems, probably from Eastern origin, and something which relates to the Chinese remainder theorem. A lot of recreational problems, like men walking, finding a purse, and they're comparing their own money. This originates probably from Indian, that is first in Mahavira's work. Men buying a horse and they do not have enough money, and so on. Cistern problems, someone goes on a business trip, and legacy problems. So these have no practical purpose unless learning mathematics. Geometry is mostly concerned with practical geometry. Measurement, here are some examples of measurement of a solid, and here is the gauging problem, in which special sticks were designed with a non-linear scale, of course, to measure the volume contained in the barrel. The algebraic problem solving is quite interesting. In all these manuscripts they follow a very strict, rigid rhetorical structure. It can be divided in 6 parts. You have the problem enunciation, then they choose some quantity of the problem as the unknown, the causa. Then you have some manipulation of polynomials. They construct an equation, and this equation corresponds with the canonical recipe for solving such problems. Then the root is extracted, and they do a numerical test. I quickly go through an example here. It's a very simple problem from one of the earliest manuscripts on algebra. Someone goes on a business trip, and he makes a profit of 12 on the first trip, and in the second trip he wins in the same proportion, and he ends with 54. I want to know, this is also typically the rhetorical style, how much he started with. He starts, in this case very simple, the beginning capital is the unknown, the causa. Then you have some manipulation, which amounts to the proportion the profit after the first trip relates to the beginning capital as the profit on the end of the second trip to the beginning of the second trip. Then from this they manipulate so that they arrive at an equality, and this equality leads to a quadratic equation. And for this equation they apply the standard rule. They usually repeat the rule also in the treatise, and in this case, and this is different from the Arab version, they normalize the equation by dividing by the coefficient of the square term, so a, but in this case it's 1, but still they do it. So they follow this rhetorical style and they divide by 1, and then apply the rule, and they come to a value. Usually they recognize only one positive root of the equation, and then they use this value in the enunciation of the problem to see if it fits. So it's a verification, a numerical verification of the reasoning behind it. So now, what did Abbacists contribute to mathematics or their society? Well, this is, I will go into detail on the last three things, but in general, they educated a very large portion of society, the merchant class, to reckoning with these new Indo-Arabic numerals. This was a complete new system, different from previous practices. If Viet writes in the end of his Isagoge to leave no problem unsolved, well, partly it's based on this practice of problem solving. They applied algebra to all kinds of problems, and they indeed tried to solve every kind of problem which was related to their practices. They helped in the expansion of the number concept. They had a very liberal view about what a number should contain, and this included the acceptance of irrational numbers, and by the end of the period also the beginning of the acceptance of isolated negative quantities. They introduced a second unknown to solve problems, linear problems with multiple unknowns. They also did some preparation for the solution to the cubic equation, which came in the next century. And then I take out some three interesting things. Creation of value. We're talking about a context here in which cities had different monetary systems. The gold content of coins in different cities was different. Also the units of measure were different within the region in which they were trading. So nothing was really fixed. It was a very vague idea of value. There were no standards for determining time, length, or volume. So everything had to be compared. And what the Abbaco tradition contributed is the idea that there can be an objective measure, an objective value, and this is also essential for the mercantile system at the time, which is based on trust, fairness, and objectivity. And to be able to exchange, you need some kind of objective value. Even in barter problems, in which you exchange goods, they talk about one fair value. And this corresponds nicely with what Foucault writes in his chapter on mercantilism in Les Mots et les Choses, that this society contributed to the idea of value. He doesn't talk about the Abbaco tradition, but it nicely connects how they assisted in this process. Also interesting is that in all these problems, the arithmetical and the algebra problems, there are no approximations at all. Everything is expressed in sometimes by irrational quantities, but never there is an approximation. Every value, every solution is an exact value. Also an important contribution, and this is only recently recognized, is the beginning of symbolism. There were several attempts towards symbolism, but I found in a family of manuscripts a first explicit reference to symbolism, in which the author solves all problems in a rhetorical way, standard way, and then adds a symbolic solution. And the symbolic solution already existed as a kind of scratchpad calculations done usually in the margin of these manuscripts, but he puts it in boxed elements within the text. And this Abbaco master calls it the two ways per scrittura, or rhetorically, and figuratamente, symbolically. And he says, I show this after he put the symbolic solution. I showed this symbolically, as you can understand from the above, not to make things harder, but rather for you to understand it better. I intend to give it by means of writing, as you will see soon. So he first gives a symbolic solution and a rhetorical one. And he says it's for you to understand it better. So my interpretation of this is that these symbolic solutions, which are not part of the explanation, they are non-discursive, and they act in the same way as some other illustrations they put in, like schemes for multiplication of binomials or for operational fractions. These are non-discursive elements which are put into the text for epistemic reasons. They give an additional epistemic function to prove the correctness of the operations they're using in the rhetorical text. And this is, you can say that the first use of symbolism acts in the same way. It's only later, a few centuries later, that symbolism also gets a discursive function. It becomes part of the reasoning itself, but this is not true in this context. And then, sorry, I have to go back home.
Use the room?
No, it doesn't work. I don't know why.
Back and forward. You know.
Okay, and then the last is concerns the use of tables, and at some point this even goes into idea of mathematical induction. So they use a lot of tables in the manuscripts, and this is a kind of survey of the use of tables. I distinguish them in synthetic and analytic. Synthetic is observation, tariffs and taxes, the finance of gold coins, they're all full of tables like that. And analytic are derived from certain calculations, like interest tables, and also some about number theoretical properties. Here's some example. This is a core table. This is a compound interest table. They have tables for several years of interest with different increments of interest. This is the well-known chessboard problem, which you put one grain on the first, 2 grains on the second, and it's a summation of a geometric progression. And they use the table as a calculating device, and also as a proof of the solution. This is about arithmetical progressions or squares. And this is the interesting one. It's these are remainder tables. The earliest occurrence I could find is from the end of the 14th century, and they refer to it as the table of infinite numbers or numbers without end. So this is the first reference to infinity in this kind of manuscript. And they start from 8. I have a better example from a different manuscript. It also appears in this family of manuscript. They start from 8 and they go to 113. And what you see is numbers, and these numbers are the remainders for certain moduli. And they use the modulo 3, 5, and 7. And they start with 2, 3, 1, and then exhaustively calculate all the moduli, all the remainders for this moduli. And they see then that 2, 3, 1 appears here again. And from this, this is related to some kind of problems on remainders. So they ask to find certain kind of remainders. And in the second example, they ask to find repeating remainders. Now, this is of course related to the Chinese remainder problem, but it's not used here. It's just an exhaustive method of finding this. And they come to the generalization in which they say, arrive at the idea that there are an infinite number of solutions. And the table is used as first to find these remainders by an exhaustive method, to find repeating solutions, and then it acts as a proof for the generalizing step, which is a first example of mathematical induction, which is usually related to Pascal in 17th. So I would say Abbaco tradition is a good example of mathematical culture. If you take this criteria of Alan Bishop that enculturation is very important for mathematical cultures, then they had this formal program of educating a whole class of merchants in that time, in the 14th and 15th century. It had a very important influence on the development of that society and the economic system, and it paved the road for the later transformation, which is usually associated with the end of the 16th century, the beginning of symbolism, abstraction, and expansion of the number concept. And it had a huge influence also on humanist mathematics in the later century. Okay, thank you.
Was the introduction of the Abbaco culture problematic in any way, or was it just
There was some criticism for using the Hindu-Arabic numerals. You find that because, especially for official reasons, like notaries, they still used the Roman way of writing numbers, with the idea that it can be counterfeited, can be fixed, and this is not a real reason. That's the only criticism I could see. Otherwise, it was happily accepted in supporting changes in